So in an attempt to get these four parameters down, so this is just essentially a repeat of what the definitions in the book are. Can you copy this? Why don't you join this table? Okay, so again, these are on Canvas. We have four parameters. So we know very well what it means for two vertices to be independent. The two vertices are independent if they are not adjacent. I just copied these from the book. If a set is independent if no two vertices are adjacent, so pairwise they're not adjacent. The independence number, denoted alpha of G, is the order of the largest independent set. A matching, so again, so we have vertices are independent, so there's no edges between them. A matching corresponds to a set of edges which share no vertices. Okay, so we can think of an independent set of vertices as a set of vertices that have no edges. Here we have a set of edges that share no vertices. Okay, so that would be that's a matching. And then the independence number is the largest set of independent vertices. And the matching number is the maximum order of a matching in a graph. And we're going to go through a couple of proofs today, relating these, at least two of relating these four parameters, but not all to each other. And then we're going to continue looking at examples from the book to try and find independence number, matching number, and the vertex cover number and the edge cover number. Okay, so we'll work on that in a few minutes. But so again, we've got four definitions. The independent two vertices are independent, two edges are independent, or they form a matching. A vertex cover. So notice a vertex cover, and I'll use his notation of V cover, if each edge is incident to a vertex in Q. So in other words, the vertices cover the edges, and an edge cover is a set of edges where every vertex is covered by at least one of the edges. Okay, and then the parameters that go along with it are alpha prime and beta prime. So we have four parameters: alpha prime, the order of the largest independent set of vertices. Alpha, the order of the largest set of independent vertices. Alpha prime, the maximum order of a largest set of independent edges, or largest matching. Beta is the vertex cover number, so it's the order of the smallest. Notice it's the smallest number of vertices that cover edges, and then the edge cover number is the smallest number smallest number of edges that cover all the vertices. Okay. So we've got these four different parameters, and as some of you noticed the other day, there's a relationship between these. So what I would like to do, you've got these definitions. I would like to, at least before we prove anything about these, I'd like to go back to page 298 and 299 and talk about 1 through 4. So 1, you needed to find maximum matching and independent set and so forth. 2, the same thing, except now you're just looking at the class of trees. So take a couple minutes. So again, compose your answers to 1 through 4. Let's say 1 through 3, and then we'll talk about how these parameters relate to each other. Okay, everybody need another one?
But they go to these pictures.
Yeah.
So that's 298. It's very quiet.
I think it's not matching, the maximum matching is 4. Yes.
So do you have that one?
5, 4, 5, 7.
These five work.
4.
Oh, no, you're right. So Z will cover this side, this side, this side. All of
There's
those.
1, 2, 3, 4, 5, 6, 7 to matches cover. And
And
then
then Y to get to Z. And X to get to the next side is 2.
yeah, there's 2 more for the district. But you didn't cover this one, this one, this one, this one, this one.
Right, but once you say X and Y, you already cover
Oh,
X. And once you say Z, you already cover X.
yeah, so you still need to cover it.
We don't need to do it, but we need this one, so you could either choose either one of these. And then you would use this one to cover those two.
No, you just choose
Either one.
either one of them. Yeah.
And then this one.
The context.
So you get 5.
And choose these 2, cover these 2.
And up. Yeah.
I think you can. Okay, yeah.
So 5?
1, 2, 3. Yeah, 5.
Okay. And then what did you do on, these are labeled here because they have an ABC and then 1, 2, 3, 4. What did you put for part B? Because on part A you said, no, it doesn't have a part B.
Yeah. And this, do you have number on this one? Like a, okay, the little picture of this. The number.
I think you got that right.
This one in the question.
Yeah, my group did not get that far.
Okay.
So I would need to do that one.
Yeah. The maximum matching is the
Largest matching alpha pi. I just have to do an abbreviated version. So on part B, what is the size of the maximum match, and then G did you get 4?
4.
Yeah. And then, does this mean you're supposed to do both of them?
There's 2 pictures
Yep.
same question, in the same question.
Same question.
Oh, so I was supposed to answer a separate question in this one.
No. No perfect matching.
Right, but I didn't answer that. I only answered this one.
Oh, yeah.
I was supposed to do both, right?
Yeah.
Okay. And then top graph. Bottom graph.
Nico.
And then did you have a maximum matching on this bottom graph?
Yeah.
What would you get for that one?
5.
So it can't have perfect
No.
matching. And how are you catching that quickly?
Like, so for the bottom part, which is like 1 by 1, and you look on this 6 spot, like a plane, so you can't have any matching with the 3 points because they match on the bottom one. So it's like So it's like
Those are out.
they're
So we
out.
can
So
only
we
do
just
this one and this one.
yeah. So we just left like a 3 triangle. So you just choose whatever 2 of them.
Mhm. So 1, 2, 3, 4, 5.
Yeah.
Okay. Okay, and then we didn't do A, B, C, D for the second graph. Is that what you were asking me? The maximum matching.
The maximum matching is that this one seemed like the part B.
Yeah. Don't you think the same thing? Yeah.
So we already did this one from this graph.
So the maximum matching was 5. Maximum independent set. Which 5 did you find?
Oh, I just write this one down first.
Oh, sorry.
Because there's 2 like. Well,
Okay, you all comfortable at least a little bit with the definitions? What it means for a vertex, for a set of vertices to be independent? Means that there's no edges between them. Independence number is the largest such set of vertices. Okay? The matching number, so that's a set of edges, no two of which share a vertex. And the matching number is the largest such maximum order of a matching. Then there's vertex cover, which I will always pretty much call a vertex cover. I may just call it a cover. And here we're looking for the smallest vertex cover. So we're covering, what are we covering? We're covering vertices. So with a vertex cover, we're covering we're covering the edges with vertices. And for the edge covering, I'm covering the edges with one more time. The vertex cover is covering the edges with vertices, and the edge cover covers vertices with edges. Did I say that right? I think so.
I think so.
I have to go listen to the recording. Okay. So the covers, the idea of the covers are a little are different than independence. Independent set. So alpha of G is simply the largest set of independent vertices, and beta of G is the largest set of independent edges. That's that's alpha prime is the largest set of independent edges. Okay, and then the covers, let's try alpha prime. And then the covers, beta and beta prime, are the largest vertex cover and edge cover. So again, for a vertex cover, every edge is incident with one of the vertices. So a vertex cover covers edges, and an edge cover covers vertices. Vertex cover covers edges. Covers edges, and edge cover covers vertices. So again, I'm gonna find a set of vertices, so every edge is incident with at least one of those vertices. Edges, I'm going to find a set of edges so that every vertex is in at least one of those edges. Okay? And again, one of the reasons I want to go through some examples is to give you a feel for what these parameters are. And then we'll actually go through some results about them. Okay, so the first one. So we'll just go down the questions as asked. Does G have a perfect matching? Perfect matching. Okay, so the largest set of independent edges. So independent edges, so I have edges that don't share any vertices. They're independent. They don't share vertices with each other. So that's the picture of what an independent set of edges looks like. If this is all the edges, if this is all the vertices, then this is called a perfect matching. And you might think of this as being, if you're trying to pair, if you look at it thinking of an application, so we're trying to pair off medical students with medical schools. And we probably want to pair off as many of these as possible. Then if I compare off all the medical schools, if there are K medical schools with K students, and they give you some sort of ranking, then that matching would be perfect. So the idea of perfectness in this case means that everybody is matched up. So we have a matching is perfect if all the vertices are matched up. So in particular, if this is a graph of order n, and it contains a perfect matching, what can you tell me about n? It's a loaded question. It's not.
Even?
It's even. Okay? I've got a perfect matching, so there must be an even number of vertices. Okay? If it contains a perfect matching. Okay, and what we're going to do is we're going to look at what trees contain perfect matchings, we're going to look at different examples. Okay, so back to problem number 1. Does G have a perfect matching? Mm-hmm. So we're looking at GA and GB.
No,
How do you know that G doesn't have a perfect matching?
because alpha prime is not equal to the number that the
To n
vertices
over two.
divided by 2.
Okay, so how many vertices are there?
10.
So there are 10 vertices, so that means you can't find a matching with 5 edges in it. Okay, one more time, there's 10 edges here, but 10 vertices. By the way, if I had 11 vertices, then you immediately know you can't have a perfect match. Okay, we can't match everybody up because there's an odd number. So I have 10 vertices, and I can't find, so can someone give me a proof that I can't find the perfect matching? Or kind of argue with me that I can't have a perfect matching in graph A.
You could, well, in 2 cases, you could assume that, let's say, for example, AZ are or are not.
Wait, AZ?
Yeah.
Oh, AZ. Okay,
Yeah.
you're gonna use. So you're gonna look at 2 cases. If there was a perfect matching, A would have to be matched with little a, would have to be matched with something.
Right.
And you're looking at the 2 cases, if A is matched with Z, or if A is matched with X.
Right. And in both of those, I think we can show that it doesn't work.
Okay,
So,
so you think,
yes.
okay.
So assume that that AZ is in our matching.
Okay,
Okay, then BX would have to be in the matching.
Okay.
Because, well, hopefully that's obvious. And then if BX and AZ are in there, then CY has to be in the matching.
okay,
And then D cannot be in the matching.
okay, okay. So rather than looking at 2 cases, let me, that's fine, but let's look at the 4 vertices. Sorry, A, B, C, D. Yeah, there's a reason they label them A, B, C, D. Okay, if there was going to be a perfect matching, how big would their neighborhood have to be? If there was going to be... Hey. You know, you were plugged in. What's the problem? Okay. Okay, so if A, B, C, D had a perfect matching, sorry, if this graph had a perfect matching, then how many vertices would A, B, C, and D have to be adjacent to? At least 4. Okay, but in fact, A, B, C, D, how big is the neighborhood of A, B, C, and D? 3. Okay, so there is another proof, essentially the same proof, that there is no perfect matching in little a. What about little b?
Oh, okay, so answering the question.
Remove this graph. Keep this graph.
5. And I got 5.
It's going to be a long class.
Nope, 7.
So I got these 5.
And what are you thinking? I don't hear a lot of talking.
To B and C.
What he said.
You have B and C, right?
B and C.
So how about this one and this one?
Well, no, I got some.
So let me ask a question. If there was a perfect matching, what could you tell me about X, Y, and Z?
At least 3
They have,
at least 3.
okay, but so where are the 3 neighbors of X, Y, and Z?
P, W, Q.
Okay, so if there was a perfect matching, then X, Y, and Z would have to be matched with P, W, and Q. One more time. If there was a matching, perfect matching, then X, Y, and Z would have to be matched with P, W, and Y. Sorry, P, W, and Q. Okay, so if P, W, and Q are matched with X, Y, and Z, what's left? What edges are left for U, A, and B?
2 triangles.
So I'm left with, in fact, with 2 triangles. So is there any way to match up A, B, U, C, D, V?
No.
No. Okay, so this contains no perfect matching. Okay, and if we wanted to find the largest matching, it would be 1 less. There would be 2 points that are unmatched in both of these. Okay? Questions? Okay. What is the size of the maximum matching in G? Well, that I just sort of gave that to you. Okay, so we've done a maximum matching in G, which I'm guessing these are the graphs G. Okay, a maximum independent set. Okay, so let's see. So one more time, a maximum matching in this graph.
We have 5.
We have 5. Okay, so this graph has 10 vertices. Is that right?
Mm-hmm.
And you have 5, a maximum matching
Oh,
of
sorry, no,
4. Okay, so let's actually find those four. So, not yet, not yet. So, matching. So here's a matching with 4 edges. And I know I can't have a matching of 5 edges. Okay, we already went through that. Okay, so that's a maximum matching in this graph. What about a maximum matching in that graph? We know we can't have a complete matching. We don't have a perfect matching. Five. Want to tell me or you want to? You said you were going to use these 3 and these 2?
Yeah, sure, this is fine.
That's what you were going to say.
Definitely.
Okay. And again, we know we can't have a perfect matching. This is as close to perfect as we can get. Some people might call this near perfect. We're not going to use that notation. Okay, so we have, this is the largest matching in each of these. Okay, so we have a maximum matching. How about a maximum independent set? So remember, what's an independent set? Someone has to tell me what an independent set is.
Not adjacent to.
So they're
Not
vertices or edges?
vertices.
Vertices. So an independent set, I'm looking for vertices so that no 2 are adjacent to each other. And I'm looking for the largest one.
5.
So do we have 5? So let's see. Tell me if is that a good start?
Yeah.
Okay, so there's 5 independent vertices. Okay? Can anybody, is there 6?
Yep.
Someone has 6? Anybody else have 6? Okay, let's hear them.
Instead of the one at the top, do the 2 that are adjacent to it.
Oh, but they're adjacent.
Oh, God, what have I done? I retract myself.
All right, so you retract your 6. Okay, so it looks like the independence number is 5. Independence number is 5, and let me make sure I get it. The largest set of independent edges, alpha prime, is 5.
It's 4.
Alpha prime is 4. 1, 2, 3, 4. Okay. All right. Let's see. How about a minimum vertex cover? Okay. One more time. Let's look at what a vertex cover is. Vertex cover is a set of vertices so that each edge is incident with some vertex in Q. So I'm looking for a set of vertices that cover the edges. Vertex cover. Set of edges that cover the edges. Notice they don't have to be independent vertices. By the way, is a set of independent vertices a vertex cover? So here's a set of independent vertices. Does it cover all the edges? No. Okay.
There's 2 more.
Which edge is not covered? A lot of edges. These 4 edges are not covered. Is that right? Are there others? I think all the rest are covered. So there's a lot of edges that are uncovered. Okay, so I'm looking for one more time, I'm looking for a set of, I'll find it, a vertex cover. So I'm looking for a set of vertices so that every edge is incident with a vertex in that set.
All the other vertices.
So what was that?
Just choose all the other vertices that aren't in the independent set.
Okay, so I'm going to take these 5 and then all of them?
No, all of them that are not in the independent set that you chose.
Oh, I see. So those 5 vertices, let's make sure I'll try blue. Maybe. Okay, so here's a set of 5 vertices. Is every edge covered by one of those 5 vertices? Okay, and I need, so the vertex cover number is defined to be the minimum order. We can't find 4 vertices that cover all the edges? So again, vertex cover number, so I need to find the smallest set of vertices that cover all the edges. So 5 looks like a good candidate.
Is it always the set of vertices that are not in the independent set?
What do you mean? What do you mean? What?
So the ones you have circled are in the independent set,
So the ones I have circled are in the independent set. Mhm.
and the remaining ones were,
We're not.
yeah.
Well, I mean, okay, so what is it, one more time, what is the vertex cover number? Means that every edge, well, look, in the independent set, in this independent set, can there be any edges?
No.
No. So, gee, that sounds almost like a theorem. Okay? Almost. How many vertices in this graph?
10.
Okay, so let's just note alpha plus beta for this graph is equal to 10. For this graph. What about the other one? Let's see, did we find an independent set in the other one? Sorry, did I find an independent set of vertices in the other graph?
No.
This graph. So we better do this. We found an independent set of edges, so now I need the maximum independent set of vertices in this one. And let's see, this is B, and this is A, right?
Yeah. Notice if I didn't put AB.
So we know that the largest set of independent edges is 5. Largest set of independent vertices? 5?
Yeah,
How do you get 5?
the bottom 3.
Okay, bottom 3.
In area, like,
And in fact, pretty much any 2 up here, right?
yeah.
Just to be different, I'll choose those. Okay, those are independent vertices. Okay? So, let's see, so what do I know? I know that alpha,
It's
5. Alpha prime,
5.
5. Okay, so now beta. Largest set of independent edges. Right, so that's the matching number. So I want to find a set of edges so that no 2 share a vertex.
You did that. We did that.
We did that one with alpha.
Oh, but I want to find the large, did I do that with?
Yeah, we need the vertex cover.
I need a vertex cover. Sorry. Sorry, vertex cover. Smallest number of vertices that cover all the edges. Cover all the edges. Do I have any, by the way, if I look at the blue squares at this point, do I have any edges that are not covered? A what? Did you say a lot? Okay, so one more time. So I have 5 vertices. They don't cover all the edges. Can you tell me an edge that's not covered? Point, tell me.
The triangle.
So like this edge,
Point like anything.
is this edge covered? Yeah, this
Yeah.
edge, is this edge covered?
No.
Okay, so this edge is not covered. Let's see, then this edge is not covered. There are more. This is kind of a lot. Any?
She said 7.
She said 7. Okay, so you think that the number of edges that cover, let's see, so what are, we're looking for? We're looking for the number of vertices that cover all the edges. What would the set be?
The 3 on the middle one.
Okay, so these 3,
Wait.
these 2,
You said the vertices cover, right?
oh, vertices cover, these 3?
The middle.
The middle, okay. So let's see, I'm running out of colors.
Green.
Okay, green. So vertices that cover all the edges. Those 3 cover a lot of edges.
And either 2 vertices in each triangle.
So wait a second, what's wrong with, so if I pick that,
And you pick the other one.
does that cover all the, do we have all the edges covered?
No, there's
No, this is, yeah.
either 2.
Okay, so I gotta pick 2 in each of these.
Yeah.
So it looks like 7. So what's that, the parameter is beta. Looks like 7. Okay, so what's left? So I need beta prime. What's beta prime? I'm gonna put it over here,
Edge cover.
because I've run it out of. Beta prime is the edge cover number. Okay, let's read that. Edge cover. Every vertex is incident contained in an edge in W. So can you find a small set in this one? Can you find a small set of edges so that every vertex is incident with one of those, at least one of those edges? Okay, let's start with the green ones right now. So there are vertices that are not incident with some of these. How many? 2. In fact, this one and this one. So I need to certainly, it looks like I probably need to add 2.
Yeah.
Okay, so it doesn't matter which, so here's one, and let's say this one. Now every vertex is covered by an edge. Every vertex covered. Now, I mean, there's a lot more work to show that this is the smallest set, because that's what you need to find, the smallest set. But let's imagine that it's equal to 6. Let's just, what the heck? Okay, one more. What about beta prime over here? Beta prime. So let's see. Same thing, same problem. I have 2 vertices that are not covered by these edges. Everybody sees the 2 vertices that are not covered by these 5 squiggle edges. It's going to take a long time if I have to do that. Okay, so there are 2 vertices not covered by any of the green squiggle edges. There's no edge between them, so I need to add probably 2 more edges. Okay, so it doesn't matter which ones. Just to be different, let's add that now. Any coincidences about these 4 parameters? So just for the heck of it, for graph A, what's alpha plus beta?
10.
What's alpha prime plus beta prime?
10.
10. How many vertices in this graph?
10.
You think that's a coincidence? Coincidence or Theorem. Yeah, which one? Theorem, okay. So does it work for this one? How many vertices in this graph?
12.
12. What's alpha plus beta?
12.
And what's alpha prime plus beta prime? Yeah. Okay, so we'll hopefully before we get out, we'll show that that's the case in general. Okay, so we found the a minimum vertex cover, a minimum edge cover, so we did that. Okay, well, before we prove this, let's talk about trees. I mean, you know, rather than talk about trees, before we talk about trees, draw a graph on 12 vertices. Draw your favorite graph on 12 vertices. Your favorite graph. Don't choose your neighbor's favorite graph.
You would say that's not very easy.
And make it interesting. So, like, probably a complete graph wouldn't be very interesting.
I love that movie.
12 vertices, your
Do what?
favorite graph.
What was that?
Did you ask for a tree?
A graph. At this point, a graph.
Oh, there's any graph.
Any graph.
Path graph too uninteresting?
Yeah.
Do what?
Is that path graph too uninteresting?
Okay, ask me anything about that.
It'll work.
Yeah.
It'll work. Okay, and we're gonna have to look at trees in a few minutes, so, let's start with this.
Yes. And seeing all the edges, there's no way.
How long path? Tell me when to stop.
Like 12.
12?
You go one more.
13, we gotta have 5 numbers. Okay, by the way, that's, if you look on down, 2 asks you to do this for any tree. Is this a tree?
Yes.
Well, how do we know it's a tree?
It's connected.
Connected,
There's no cycle.
and there's no cycles. Very good. Okay. Alpha. Alpha is, let's read. Alpha is the largest set of independent vertices. Can I pick a good number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What's the largest set of independent vertices?
7?
What? 7? Are you asking or telling me?
Okay, I'm telling you.
Okay, you tell me, because you're going to take the 1st, the 3rd, the 5th, the 7th, the 9th, the 11th, and the 13th. Or you can take some, there's lots of ways to come up with 7 independent vertices. So it looks like beta is equal to 7.
Is that
Sorry,
alpha?
alpha is equal to 7. By the way, can you cut, is there a tree? A tree, remind me, what's a tree?
Connected, no cycle.
Connected with no cycles. Is there a tree that has more independent vertices?
Yes.
There is?
Like a star.
Oh, like a star. So, there's a star on 14 vertices. I picked 14 because this was on 14. It has independence number 13. By the way, let's see, I want the vertex cover number. The minimum order of so I want to cover vertices with edges. Well, I mean, look, we kind of had a theorem here. Kind of thought we had a theorem.
On the left.
Beta must be 7.
So beta must be what?
7.
7? Wait a second, how many vertices does it have?
14.
Okay, and what's alpha?
7. You mean in the top one?
Yeah, that's the top one. Alpha 7 here. What's alpha here?
13.
Okay. Sorry. Here, see, I wrote it down there. I have it. So if your conjecture is true, what's beta?
The top
On
one.
the top. Sorry. Okay, so
Beta top, beta bottom.
so I'll put a question mark for the time being. What's beta for the star? 1. Is it 1? What? Remind me, what's beta?
The
Vertex cover.
cover.
So every edge is incident with one of the vertices in this cover. So which vertex would you choose here? The middle one. Okay, so again, beta is covering edges with vertices. That vertex covers all 13 edges. It's looking more and more like a theorem. Okay, what's the smallest value? So I'm still reading on number 2. Okay, the least value of beta of t. So I have a tree of order n. Better read what beta is again. Beta is a vertex cover so that it's a set of vertices. So every edge is incident with some vertex in the set. Can it be larger? Can it be smaller than 1? In a tree. So I'm going to guess this is looking pretty good. Okay, so it can't be any smaller than 1. It can't be 0. You can't have a tree, a non-trivial tree, and here's a trivial tree. Well, even that would have 1, right? So I guess there are 0 vertices in an edge cover. So you have to have some edge in it for it to be interesting. Okay? You don't need any edges actually to cover all the edges. Sorry, you don't need any vertices to cover all the edges since you have no edges. So let's make it interesting. Okay, so the smallest it can be is 1, and what's the largest? What's the largest it can be? Okay, so again, I want a set of vertices. One more time, so I need a Do you want?
I'm sorry.
No,
we
I
can-
have.
You have one,
just
okay.
discussed it.
Okay, so I want a vertex. What's the largest it could be? So a vertex cover is the minimum order of a vertex cover. So I want a set of vertices that cover all the edges. On 14 vertices, can you have more than 7? Can you have less than 7? Let me ask it that way. Can you give me a tree? Let's start with this. This tree has vertex cover 1. Can you give me a tree that has vertex cover 2? A tree on 14 vertices.
Can you take one edge out?
Do what? Well, that's a lot. It's a lot. I should have made it small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we need. I think that's what I want. Let's look at that. Is that a tree?
Sure looks like one.
Looks like a tree. No cycles. It's connected. And what's the vertex? What's the vertex cover number?
2.
How many vertices do I need to cover all the edges? Can I do it with 1?
No.
Can I do it with 2?
Yes.
Okay. Can you find a tree that has vertex cover number 3?
Just add 1 more
Just add, oh, careful.
to the right.
I want a graph I want a tree on 13 vertices. So like this? Careful.
That's still 2.
Why is that still 2?
The middle one, and then the middle one in the path,
Okay, so,
That
so
one.
it's still 2.
and then 2 over. And then 1 more.
Okay? Any other candidates? Of course there's other candidates.
There's another one on there.
What about this? Okay, so in your tables, I want you to, again, I'm looking at problem number 2. So I want you to find a sequence of trees that contain that have alpha of t as large as possible, alpha of t as small as possible, and then can you achieve every value in between? Okay, so one more time, I'm looking at problem number 2. T is the family of all trees. Let's just stick with trees of order 13? 14. Trees of order 14. Okay, so I'm just going to look at trees of order 14. What values of these 4 parameters are possible? Okay, what's the largest value of alpha of t? What's the smallest value of alpha of t? And then can you attain any value in between? Again, I'm looking at problem number 2. What's the largest value of alpha prime? What's the smallest value of alpha prime? And can you attain every value in between? And then what about the beta t and beta prime of t? I'm not sure why he changed largest to least, but
So if n is equal to 14, then the largest alpha of t is 13,
Yeah.
and the smallest alpha of t is 7, which is n over 2. Yeah, let's see if that's consistent. And then the largest alpha prime of t is the largest matching.
Oh, the largest matching is, and then 2.
it's pretty quiet.
This would have to be
Lower 2.
we need to go. Yeah, it's going to be an over 2 because we would do 6, 7. We could do largest matching. But it's probably always number 3.
The largest of all the teams.